prior to getting into the theoretical exercises, I want to state this theorem. And afterwards, I'll say why all these theorems are very important. If A is a square matrix, n by n matrix, then A is non-singular if and only if AX equals B has a unique solution for every n by 1 matrix B. Okay. If this always has a unique solution, regardless of what the right-hand side numbers are, then A is non-singular. Now, here is the reason why you need to know a lot of these theorems cold. This list that I'm about to write, the list of equivalences for a non-singular matrix, list of equivalences for non-singular. That is, the list that I'm about to write, they all mean non-singular. That is, they're all equivalent. They're the same statement. If A is non-singular, of course, A is non-singular. If AX equals 0 has only the trivial solution, that's the same as A is non-singular. Sorry, yeah, A is non-singular. The third one is if A is row equivalent to I. That is, if you can reduce A to the matrix I, then A is non-singular. All these three statements say the same thing. If somebody tells you A is non-singular, you can hear A is row equivalent to I. If you hear AX equals 0 has only, if somebody says to you AX equals 0 has only the non-trivial solution, you can hear A is equivalent to I. It wouldn't matter. Or A is row equivalent to I. Or you can hear A is non-singular. They're the same. These three statements are the same. And now we can add the last theorem. AX equals B has a unique solution for every n by 1 matrix B. Okay, that completes the section on the inverses. Now we're going to do some theoretical exercises. This is where the fun begins. If your book has theoretical exercises, then by all means, attempt to do them. That is how you learn linear algebra. You can do the proofs, then you can do the mechanical problems on an exam. Okay. Suppose A and B are n by n matrices. And you come to know that AB is a 0 matrix. When you multiply A by B, you get the n by n matrix where each and every entry is 0. if B has an inverse, that is, if B is non-singular, then what can A be? What can matrix A be? The answer is, I hope the answer is almost obvious. You have AB is equal to 0. AB is equal to 0. 0 matrix. And all you're really told is that B has an inverse. So why don't we multiply by the inverse? AB, B inverse. I can move the brackets. Instead of bracketing the first two, I can bracket the last two. And 0 matrix times any matrix of the right size. And if B is n by n, 0 is n by n, and B inverse is n by n. I should have said if A and B are both n by n, then B inverse is n by n, and the 0 matrix is n by n. That is, this product is a 0 matrix of size n by n. Okay, but B times B inverse is I. It still equals 0. And A times I is 0. Sorry. Here, A times I is I, which is 0. And there's the result. If A times B is 0 and B inverse exists, then A must be the 0 matrix. If AB is 0 and B is non-singular, B is non-singular, if the inverse of B exists, if B is non-singular, if B is row equivalent to our I, and Bx equals 0 has only the trivial solution. That list that I just wrote, and Bx equals little b, has a unique solution for each b, n by 1 matrix of size called B. The size of little b must be n by 1. Okay. So if you're told AB equals 0, like you are up here, and you're not necessarily told that B is non-singular, but if you're told any of these four, namely the last three, if you're told the last three or even the first one, then A must be 0. You need to know their equivalences. It's very important. Remember how in my final, my instructor asked me to write down all the equivalencies for non-singular, and by error I wrote all the equivalences for singular. And based on my grade, he didn't hit me up too hard, if at all, on that. I never did forget that. Okay. We want to show, we want to prove. We want to show that if A is a non-singular symmetric matrix, then A inverse is also symmetric. Oh, what on earth happened there? Okay, sorry about that, folks. Show that if A is a non-singular symmetric matrix, then A inverse is also symmetric. Okay. So proof. Now whether you write it in the proof or on the side, you should write down what things mean. A is given to be non-singular, which implies A inverse exists. Okay? And A is a non-singular symmetric matrix. That is, A is symmetric, which implies A is equal to A transpose. And these two are given. You want to show that A inverse, so this one we don't know, we want to show that A inverse is symmetric. That would imply that the matrix is equal to itself transpose. So that is what I want to show. I want to conclude that A inverse is equal to A inverse transpose. Okay, so A is a non-singular symmetric matrix. So A inverse exists, and A is equal to A transpose. I wrote down what the first two statements mean. A inverse exists, and A equals A transpose. Okay. Now, A does equal A transpose, but that's the same as, I guess I can just put the arrow to the right, but that's the same as if two matrices are equal and the inverses exist, then their inverses are equal. The inverse of this equals the inverse of that. Now, I know the inverse of A exists, because A is non-singular. You may say, come on, how do we know the inverse of A transpose exists? It's a fair question for beginners, but the answer is because it's A. This is A. It doesn't look like A, but it's A. If the inverse of A exists, then anything that equals A also has an inverse. All right. Now, this is where it all comes together. We had a theorem that says that you can switch those. That is, we get A inverse transpose. Oh, you mean this matrix is equal to itself transpose? That implies that A inverse is symmetric. You have to know the theorems. You have to know that A transpose inverse and A inverse transpose, them the same. They are the same. There is no difference between them. They're equal. And if you don't know that, then absolutely, that's going to be a hard problem. On that note, that finishes up the whole video segment on the inverses.